VAV is smaller than a certain value, for example, the doubly charged Higgs boson decays mainly to a pair of like sign leptons. If the VAV is big enough, then it decays to a pair of like sign W bosons. And likewise, for the singly charged, it has a similar pattern. For low triple VAV, it's leptonic mode, and for the larger triple VAV, it's either T B bar or the W and the other bosons. Okay, so that's the signature modes of the Higgs triple model. So Andrew Akeroyd and Naveen Gore and I studied this model in the year of 2010, and we studied the discovery reach using different final states. Suppose we require 4 lepton final states, 2 pairs of like sign leptons in the final states. Then with the luminosity of 10 inverse Fendelbarn at the 14 TeV machine, then one should be able to reach up to 550 GeV for the mass of the doubly charged Higgs boson. And if you only require 3 leptons, you can push it a little bit higher to 600 GeV. So actually, Jiaming, Professor Guo Jiaming in our department was persuaded by me to start to participate in this search. And 2 years ago, they came up with this result. They only, because there are some free parameters in the model, so they only look at the 4 benchmark points. Here are the branching ratios of different leptonic modes. For this, they assume the triple VAV is small. Remember, for small triple VAV, the dominant decay modes are the lepton modes. Okay, so here they look at different typical benchmark points. And so here is in this plot, they show the current lower bounds on the doubly charged Higgs mass. You can see mostly the lower bounds is somewhere around 300 or 400 GeV, except for this one. So you can see that their search already pushed the lower mass limit of the doubly charged Higgs bosons to quite high. So instead of continuing the search in the direction of small triple VAV, why not consider large triple VAV case? In that case, the dominant decay modes are like sign W bosons, and this has not been carefully studied by our experimental colleagues before. So we start to look into this direction. And this was done with my postdoc, Takaki, and also with Xiaogang's postdoc, Koji Tsumura, 2 years ago. So here we consider the triple VAV to be as large as 55 GeV, we pick some number as one example. So you see that this red curve, in both diagrams, the red curve is the vector boson fusion process cross-section. So if it's for sufficiently large doubly charged Higgs mass, you see the vector boson fusion process is the dominant one, bigger than the pair production or associated productions. This is for 8 TeV and this is for 14 TeV. It's the same in both cases. So it looks like it's interesting to consider this possibility. And likewise, we study the experimental reach. Again, take the 10 inverse Fendelbarn as an example. Using different ways of cutting the kinematics in the final state, you can reach up to, here is 200, for the 8 TeV machine, you can reach up to like 250 GeV, or even if you include the forward jet tagging, then you can reach something like 400 something GeV, and that's for 14 TeV. But there's a problem. The problem is that it is about the rho parameter. Experimentally, this is measured to a pretty high precision, and we found that rho is more or less 1. But if we add a triplet to the, like in the Higgs triplet model, if we add a triplet to the standard model, there we add a hypercharge 1, hypercharge equal to 1 triplet. Then that will modify the rho parameter by this amount. And using this experimental number, this VAB is restricted to less than just a few GeV. So you cannot go to something like 55 that we considered before. If you add another kind of triplet, a real triplet, y equal to 0, that will modify the rho parameter as well, but with an opposite sign to this case. So it looks like there is something you can do. We just add this because this is a complex triplet. Then we add a real triplet. The combination of them can cancel each other. Turns out that's the Georgi-Machacek model they proposed in mid-80s. So that's why, as I said, that the consideration of Higgs triplet model led us to consider Georgi-Machacek model. So in this model, we have, again, this standard model doublet, we just arranged in such a way, 2x2 form, so that the SU2L, SU2R structure is more transparent. And for the triplet, we also arrange the fields like this. So these two columns are the hypercharge equal to 1 triplet, and this is the real triplet with hypercharge equal to 0. So you can see clearly the SU2L cross SU2R structure, you have this global symmetry in this model. And this is the standard model Higgs VAB, so that's diagonal. And here we also require that the vacuum expectation values of these fields are the same, so that in the end, we break this global symmetry down to this custodial SU2 diagonal symmetry, because this, by doing this, we can guarantee the rho parameter equal to 1 at the tree level. And also in this case, we don't have any restrictions on the triplet VAB. It can be as large as the as 246 GeV. If
really?
you want.
But what about neutrino-less double beta decay?
Neutrino-less double beta decay? What do you mean by that?
Well, you doubly charged Higgs, and you have to generate neutrino mass.
Yeah.
So in principle, you would have that, and you cannot. You know, if the doubly charged Higgs is heavy enough, yes. But when you say when even V delta as large as 246 J.
Yeah, but that's okay. If you tune up this triplet VAB, the corresponding neutrino couplings will be extremely small, because the product gives you the neutrino mass. It doesn't matter. Well, it will definitely contribute to the neutrino-less double beta decay, but it won't be a huge number, so that it violates the current constraint.
Wow.
It's determined that is determined.
You should show a plot for that.
Well, we didn't study that, but we thought that's obvious, because it's controlled by the neutrino mass, not by the VAB.
I'm not sure of that, but I didn't do it. So.
Okay.
Okay, so what about this vacuum alignment? So you need to
That's-
design your potential
that's
very special.
That's an assumption, yeah.
That's an assumption.
If you solve, I haven't shown you the potential. If you solve the most general entire potential, you will so when you do from the tadpole conditions, you will see that this is, all I can say is that this is one of the possibilities to satisfy the tadpole conditions.
Mm-hmm.
You have another solutions which is more complicated that can also satisfy, but we pick the simplest one. Well, that's also what Georgi and Machacek picked.
Yeah, in other words, this is compatible with the theory.
Yeah, it's compatible with the tadpole conditions.
Excuse me.
Yes.
Is our SU2 SU2R is global or
Global.
symmetry?
Yeah.
So how do you ensure since it should be violated in the cross sector to explain the top and bottom must be fine? So how do you ensure that symmetry?
How do I ensure what?
Since it is violated in the quark sector.
Quarks.
In the quark sector, yes.
So at least in the quark sector, it should be violated. So I'm wondering how the symmetry is good. For example, there is some variable correction coming from the core group somewhere there.
Okay. So you're saying that even though I assume at the tree level we have this symmetry, at the loop level this symmetry may not be exact. Is that the question? To be honest, we did a study that would be our next job to study how the radiative corrections will modify our theory. Yeah, so we didn't study that yet. Well, remember this is just this is a new physics model. It's how's that? It's not at such a serious level to consider all the details of the model. So at this point, we still satisfy ourselves at the tree level calculations. Of course, if there's really some indication of about the correctness of this model, we will pursue in this direction, of course. Okay, so here I just show you the most complete, most general Higgs potential. I don't expect that you remember any of them, but I just want to show you for the notation purposes. Here again, that's the standard model Higgs doublet mass term and the self-interaction term, and that's for the triplet mass and the self-interaction. And the others are the other quadratic terms. And here are the couplings between the doublet and the triplet. And again, just like in the Higgs triplet model, we have this term, mu1 term, that induce the VAV of the triplet once the standard model doublet develops a VAV. And in our analysis, we try to keep all these lambda terms. In most other people's analysis, they just ignore these lambda terms.
Do you have no rules for phase?
Because of this SU2 left SU2R symmetry, all the terms are required to be real. So unfortunately we don't have any phase. In particular, there's no CB validating phases. I will mention this toward the end of the talk. Okay, so just pictorially, we start with a triplet. We have a 3 times 3. Because this is under SU2 left and SU2R, so we have 3 times 3. And for the standard model doublet, it's 2 by 2. And once we break down it to the diagonal SU2, we have a 5-plet, a 3-plet, and a singlet coming from this triplet. And then triplet and singlet coming from this doublet. So the 5-plet doesn't mix anybody else, and it has this kind of spectrum. And this triplet and this triplet, they can mix through a mixing angle, theta h. Actually, this mixing angle is related to the tangent of this mixing angle is related to the VAV of the triplet to the doublet. So that tells us how much this triplet participates in the electrical symmetry breaking, right? So after the mixing, one physical triplet we call it H3. They have a common mass and H3, and the other triplets are the Goldstone bosons, which will become the longitudinal modes of the weak gauge bosons. And these two singlets can mix, and we assume this little h is what we discovered 2 years ago, and this is the heavier one. And the corresponding mix angle is alpha. So what's special in this model is that if you look at the Yukawa interactions, you will find that in the original triplet potential or Lagrangian, there is no interaction between the triplet and the standard model fermions. Only after mixing, through mixing, the triplet can interact with the standard model fermions. And here, because of, as I explained, the mixing is only between this 3-plet and this 3-plet, or these two singlets. So only this one and this one can interact with the standard model fermions. The 5-plet has no coupling with the standard model fermions. And even though I didn't write down the neutrino mass terms, but basically it's just like the Higgs triplet model. You can write down the type 2 CISO terms to give masses to the neutrinos. Anyway, here I write down the standard model Higgs standard model like Higgs HFF coupling, which can be written as the standard model coupling times this factor. Since these are different angles, presumably independent angles, so you can imagine that this ratio can be bigger than or smaller than 1. You can vary this ratio. It can be smaller than 1 or equal to 1 or even bigger than 1. And about the gauge interactions, here the allowed couplings are here. This is the standard model W with the W or Z bosons, and here the only allowed interactions are the singlet and the 5-plet. No 3-plet couplings with the gauge bosons. That's one feature. Another here this is one feature. No couplings for the 5-plet with the fermions, and here's another feature that there's no 3-plet couplings with the gauge bosons. And you can also calculate the HVV couplings, which is the standard model value multiplied by this complicated factor. And if this extra numerical factor is not there, you can see it's cosine, cosine, sine, sine. Then you can combine them to get I forget, cosine alpha minus theta or something. Then the whole factor will be less than or equal to 1, right? If there's no such a factor here. But in this, that's the feature of, a third feature of this model is this factor. This extra factor ruins that nice trigonometry relation. And in the end, you find that this factor can be, like this one, can be either smaller than 1, equal to 1, or even bigger than 1. So if you experimentally, if you measure, if you find that this coupling is bigger than the prediction by the standard model, then you know for example, 2 Higgs double model cannot be the right theory, because remember the 2 Higgs double model always has this sine beta minus alpha suppression. Instead, this Georgi-Machacek model can be the right model for this reason. Okay, so we study, basically we solve the Higgs potential to get the mass spectrum, and then we study how they decay under various different mass hierarchies. So if I define, here, so here I say that the decay pattern of the new Higgs bosons generally depends on 3 things. One, the mass hierarchy, like there are 3 kinds of hierarchies. And then the second thing is the triplet valve, because triplet valve controls how the new gauge bosons couples with the gauge bosons, right? So that's the triplet valve. And the third factor is the mixing angle alpha. In the following simulation, we just assume alpha equal to 0 to be specific, which of course you can vary alpha a little bit. It won't change the pattern too much. Then now we're left with only 2 parameters because we fixed alpha. Then we're left with 2 parameters. One is V delta. The other one is the mass difference between these two, the 3-plet and the 5-plet. So once you fix the order, like if you take the other m to be greater than 0, then the third one, the singlet, will be heavier than the other 2. If you take the other way, it will be like this. So you have three kinds of different mass hierarchies. So we did many plots in our analysis, but I just want to show you the summary of the result is that the decay pattern as I said, depends on the triplet valve and also the mass hierarchy. So again, for sufficiently small triplet valve, the dominant decay modes are still the atomic modes, just like what you saw before when I talked about the Higgs triple model. And if you go to a bigger triple valve, then the dominant decay modes are the gauge bosons. Then here we have one extra dimension, that is the delta M. So if delta M here, I think roughly the fork is at around 1 GeV. So if you have a sufficiently large, like 1 GeV to here, I think it's about 100 GeV mass difference. If you have such a big mass difference above these curves, there are two possibilities. One is if this is the mass hierarchy, then again, it's similar to here, and likewise here. But if the mass is three-plet is lighter than the five-plet, then the five-plet will first decay into three-plet and so on and so forth. So you have different decay patterns, and these are useful when we search for such particles at the LHC. Okay, so what about the current data and constraints? Here I take the data from last summer. So at that time we have these numbers, these signal strengths for the 5 dominant search modes for the Higgs boson. In particular, you see there is for the ZZ and WW, there is a difference. Of course, if you take into account the error bars, there's no inconsistency. But if we concentrate that on the central values, then you see there's some puzzling thing, because they should go hand in hand because of the custodial symmetry. But anyway, we just take the hint of this ZZ number and ask the following question. What happens if data prefer a greater than standard model HVV coupling? As I said, if that's the case, then 2 Higgs double model is out. Then you should consider the Georgi-Machacek model.
So in your model, you can make the ZZ and WW different?
No, still the same because of the custodial symmetry. So I said I cannot. We don't try to reconcile these two numbers. We just
writing in a paper.
Okay, so we take into account the following constraints. These two are the theoretical constraints. We require the unitarity of the scattering, so that, well, this has been studied by Aoki and Kamimura a long time ago. So we just take their result and put into one of our constraints. And this is for the vacuum stability. Make sure that your potential curves up at large field values. So these conditions restricts the possible values of the quartic couplings, all the lambdas you see. And then we also take into account these experimental constraints. The first one is R sub B, that is related to the Z decay, the precision data of Z decay. Because here I show you that you can have these singly charged three-plet running the loop to contribute to the Z to BB decays. And only the three-plet, because as I said, only the three-plet can couple to the standard model fermions through mixing. The five-plet has no contribution. The second thing, another experimental constraint is the S parameter. So here, no, not in this. Okay, so this plot is for the R sub B constraint. For 1 sigma and 2 sigma value, you have different upper bounds on the V delta as a function of the three-plet mass. Okay, so here I show on the plan of the mixing angles, because we of course we have to fix most of the parameters. We take the common mass for the extra Higgs bosons to be at the 300 GeV as an example, and then we scan on the theta H. Again, this is the tangent theta H is the ratio of the triplet valve and the doublet valve, and alpha is the mixing angle between the singlets. So we scan on this plane to search for the allowed parameter space at the 1 sigma level. If we only take the signal strengths into account, remember the 5 channels, the mu's, then at the 1 sigma level, we have this yellow area. And the place with the lowest chi-square minimums here. And the blue curves are defined in this way. It's the Georgi-Machacek coupling over the standard coupling for the HVV. So we have also shown the CHVV contours like this. That's if you only take into account the signal strength. Then we also impose the unitarity constraints, then these pink regions are ruled out. Then we impose vacuum stability, the light blue regions are ruled out. Then R sub B, that's above this curve. R sub B only depends on theta H. Then S parameter is here, to the right of this, now it looks like orange curve. It's ruled out. In the end, we are left with this yellow region. And so you can see that according to this, within 1 sigma level, the HVV coupling can be bigger than the standard model value by as much as a factor of 1.3 if you go to this extreme. And by varying the mass of the heavy Higgs bosons, you roughly get this. Well, the constraints are, of course, are different, but the conclusion is basically the same. You can also still go up to about 1.3. Now,
but there should be a prediction of preferred gamma gamma.
H to gamma gamma.
Well, the measured gamma gamma event rate.
But that's taken into account, right? That's one of the 5 observables that we
well,
took
but
into account.
Just saying, when you vary that C coefficient, when you say it can be as large as 1.3, you can make a prediction saying if you take this value, then gamma gamma cannot be the CMS result. Because a larger C would enhance gamma gamma.
But here we also have the charge Higgs running in the loop. So larger C means larger HVV coupling that will, so for gamma gamma you have a cancellation between the W loop.
Also enhances, unless you have
you have a W loop and a top loop, right?
Yeah.
There's a destructive interference between these two. Then now we have to add in also add the charge Higgs contribution as well. So
but
it's not so clear.
It's a bosonic loop unless
it's not so clear that we will definitely enhance or reduce. Well, all we require is to minimize the chi-square for these observables. So yeah, you're right. We should make predictions, but we thought that basically
the point is, I know you're moving towards VBF, which is fine with me for future measurement, but for the current measurement, there will be I suspect, unless there are signs of the charge Higgs coupling. Otherwise, it's a bosonic loop, so if there's no other fancy stuff, it would be enhancing the vector boson loop.
No. The coupling can have both sides.
It can have sides.
Yeah. Okay. So it's not a square of the coupling, it's a one coupling.
It's totally arbitrary?
To be yes.
The sign?
Yeah.
But he has...
well, he has a unitarity that constraint.
The charge Higgs is relatively heavy, so I guess they are not so important.
300 GeV is not that heavy.
But compared to the W, which is 80, okay, so...
In a separate study, we did consider these extra charge Higgs boson contributions to the gamma gamma, but that was done right after the discovery of the Higgs,
Anyway,
and at that time this number was bigger than
So I'm
1.
concerned only if there are